Okay, great. So I'm really happy to introduce our next speaker, which is Prashant Shenoy, who's a professor, a distinguished professor and associate dean, College of Information and Computer Science at UMass Amherst. He's been there for quite a long time, but he received his BTech degree in computer science from IIT Bombay and MS and PhD degrees from Austin. And I happen to be his granduncle. His advisor's advisor was my academic brother. So happy to introduce a relative, sort of nepotistically. His research interests are in distributed systems, networking, cloud computing, sustainable computing. He's a fellow of the ACM, IEEE, and AAAS. He won the Sigmatrix Test Reform Award. And he was also the founding chair of ACM SIG Energy and has done. Is being recorded. Right. He's done a lot of interesting work in a lot of different areas. And today he's going to tell us about CarbonFirst. So it's all over to you, Prashant. Thank you.
Well, thank you, Keshav, for that kind introduction. And it's great to be giving this talk at University of Cambridge, albeit virtually. And what I'd like to do is walk you through some of our work on sustainable cloud computing and tie it to some broader challenges that we need to all think about as computer scientists or scientists in general. So let me start with some high-level motivation for our work. So when we started working on this project a few years ago, we were strongly motivated by the negative impacts of climate change, which we are all seeing in the press far too often. And these are just some pictures I pulled from some newspaper showing increasing flooding, wildfires, hurricanes getting stronger, all kinds of issues that climate change has caused to our society. And so we started thinking, what should we be doing as computer scientists? And the second graph here is basically showing what different amounts of temperature rise as a result of climate change can do to society. And the different colored curves show the impact of different amounts of carbon emissions and temperature increase. As of now, we are tracking the top orange line, which is really the worst case scenario that was envisioned by scientists. So this was really even a stronger motivator for us to start thinking about, okay, what can we be doing about this problem as scientists or even computer scientists? So that's what got us started down this journey. Now, the main trend that I'm going to actually try to address in this talk is computing's demand, which has been growing exponentially for many decades. This figure shows many different technologies that computer scientists developed and eventually became popular, and as a result, that's caused ever-increasing demand for all kinds of computing devices, computing capacity, and so on. And towards the end here in around the 2020s, you basically see things like ChatGPT and rise of AI, which has really caused even further growth. Demand for growth. So what this figure is, these figures here show are essentially the impact of growth of AI. The left figure is showing different types of deep learning models, and the y-axis there is the amount of computing power it has taken to train those models, and the x-axis is time. And these models keep getting bigger and bigger. This doesn't even have the generative AI model. The graph is actually cut off at 2019. But the models get bigger, the amount of time it takes to train them keeps rising. That's fueling even more growth for cloud demand. And there has been some study that shows that machine learning workloads are doubling every 3.4 months. And that's a rate that's much faster than even Moore's law, and that's causing a lot of increased demand for cloud capacity. Now, although cloud workloads have been increasing in their demand for many years, For a long time, the cloud data center energy consumption did not go up. It was basically flat. And that's shown in the second figure here, which is plotting the PUE or power usage effectiveness of data centers. Lower is better. And you will see that even though cloud demand was increasing, PUE was actually dropping. And the reason for this is there are all kinds of energy optimizations that data center operators put in place, which made data centers more energy efficient. And even though they were growing in size and capacity, because you are making them more energy efficient, the total energy consumption was more or less flat for many years. Okay? Now that has changed, of course. So that's changed, and now a lot of the low-hanging fruit is gone, and the energy footprint is actually beginning to grow, which is also causing the carbon footprint to grow. So what this slide shows are the two key metrics that I'm going to talk about in this presentation. The first is energy efficiency, which is simply defined to be the energy consumed per unit of work done. And making our computing systems energy efficient is not a new problem. We've been looking at this for many decades in context of operating systems, power management, or mobile devices that are run using batteries and so on. So that problem has been looked at for a long time, and we've been using techniques that have come out of that community to make our computing systems more energy efficient. Now, in this talk, I'm going to actually discuss a different metric, which is carbon efficiency, which is the carbon emissions per unit of work done. Okay? And I'm going to argue that although these two metrics of energy efficiency and carbon efficiency are related, they are not one and the same. Okay? So I'll give a very simple example to highlight the differences. So for example, let's take a data center that is highly energy efficient. Let's say one of the ones that are built by a company like Google. They build the most energy efficient data centers in the world today. But if this data center is located in a grid region where the electricity is being generated, let's say by coal plants, this energy efficient data center will still have a high carbon footprint. So it's an energy efficient system, but it's not carbon efficient. Okay? And the reverse is also true. You can take a data center, let's say an university data center that are not very energy efficient because maybe you don't have all of the technologies that you need to have to make them highly energy efficient. But if your data center in this case is drawing electricity from, let's say, a wind farm, which is a low carbon source, then this data center is highly carbon efficient, even though it's not energy efficient. Okay? So this shows that although the metrics of energy efficient and carbon efficiency are related, they're not one and the same. And in fact, we need to design systems that are both energy and carbon efficient. And since I already said we've been looking at the energy efficiency problem for many decades, we decided to look at how do you make systems carbon efficient. And I'm going to talk about carbon efficiency really in the rest of this talk and not talk about energy efficiency, which is still an important problem. Okay, so now with carbon efficiency in mind, let's just take a look at what kind of impact are these cloud workloads that I was just talking about a couple slides ago create, right? So how much emissions might they create? Now it turns out that there are actually two schools of thought here in the research community. There's a pessimistic view and an optimistic view. The pessimistic view is shown on the left. It's basically based on that figure or the chart there, comes from a paper that computer scientists wrote in AAAI 2020, and that graph there is showing the carbon emissions of different tasks that we might be familiar with. There's a flight you take from, let's say, New York to San Francisco. That's the carbon emissions in the first bar. There's 1 year of human life, what is a average person's carbon footprint over 1 year of their lifetime is a second graph. What's the carbon footprint of your car over 1 year is one of those curves. And the tallest one is actually what is the carbon footprint of training an AI model. And you'll see that it's much higher than some of these other tasks that we are familiar with. So that's showing us that this AI workloads are having a significant negative environmental impact, and we should be really thinking about this problem carefully to make things sustainable. Now, the what is on the right is actually the title of a paper that was published by researchers at Google, David Patterson and several others, which appeared in IEEE Computer 2022. We took a different view. I'm not going to go into the paper because the title of the paper is actually going to summarize the viewpoint of the paper. And the title says, "The carbon footprint of machine learning training will plateau then shrink." Okay, so it basically said that whatever was mentioned in the first paper is really not going to come to pass, because as computer scientists, we will somehow come up with better technologies and everything will be fine because we will actually tackle this problem going forward. Now, I'll point out that both of these two papers predated the emergence of generative AI. So what has actually happened is way worse than what even the Struble paper was actually predicting. And at this point, I don't think computer scientists think that the carbon footprint of machine learning training will plateau, let alone shrink. But there are still two views of thought. One is the problem is really bad. The other is, yes, it's bad, but we'll figure it out. I think so. And you can decide where you fall in the spectrum, but I'm not going to say anything more about these two viewpoints today. Instead, I'll tell you about what we have been doing to address this problem. So the research question I'm going to focus here today is, how can we use computing to decarbonize cloud infrastructure and workloads? Okay. So that's really the focus with the motivation I provided for the rest of the talk. So what I'll do is I motivated the problem. I'm going to give you some very high level introduction to what decarbonization means, and then I'll get into our CarbonFirst approach that's been tackling this problem for a few years now, and I'll end with some future challenges that remain, and there are many that remain in this area. Okay, so let's start with some decarbonization basics. So what this slide is showing you are some media headlines that you might have seen in the press, right? So you will see that Facebook claimed that it reached net zero emissions. And then in 2020, Amazon said that they were the world's largest corporate purchasers of renewable energy. Apple says it's powered with 100% renewable energy worldwide. Google claims it's been carbon neutral since 2007 and will be carbon free by 2030. Right. So, and you keep seeing more of these press articles all the time. So one natural question you might ask is, has industry solved this problem? Why am I even presenting this talk? Looks like industry's already figured it out, right? So we need to really think about what these terms mean to really understand what they are saying. And then you will realize that the problem is far from being solved. Okay? So I'm going to actually look at these terms and define them for you. Okay? So the first term is called carbon neutral. Carbon neutral simply means you're going to buy carbon offsets from the energy market. So you're not actually reducing your emissions, you're just offsetting it by buying carbon offsets. Okay? The second term here is net zero via 100% renewables. So what this means is that you will buy renewable energy from maybe wind farms or solar farms, not necessarily near you, but somewhere through a power purchase agreement. And that renewable energy is enough to cover your electricity usage as a cloud operator for an entire year. Okay, so this is going to reduce our emissions, but I'm going to in the next slide show you why this is still not enough. Okay. The third term here, which is not shown in those headlines, but there have been more headlines that use this term, is called 24/7 matching. Okay. So what this says, or what this means is that you should be using zero carbon energy at an hourly granularity, which is more strict than the previous term, which just says that you are essentially using zero carbon energy at 1 year granularity, where your consumption is offset by generation. Okay? So this is going to further reduce your emissions. And then the last term, which nobody is using yet, but is something we should all be thinking about, is what I'll call zero carbon. Zero carbon means you are using zero carbon energy at all times, which means you are really not generating emissions at all from your operations. And that's really the holy grail of where we really need to be. So this is really a spectrum in terms of how green you are. Carbon neutral is really not that green in the sense that it's still generating a lot of emissions. Net zero is a bit better. 24/7 matching is even more gets you towards zero carbon, and that our goal really ought to be zero carbon energy use at all time. Okay? So now let me actually show you an example of why net zero using 100% renewables will still generate emission. Okay? So this curve here is showing you there are two curves here. The black line, which is really flat, is the data center demand of a hypothetical data center. Okay? And we are just assuming it's flat. It doesn't have to be, but for this example, assume that's flat. So that's your energy consumption. Okay? The y-axis here is essentially energy demand. Okay? And the green curve is essentially electricity generated by, let's say, a wind farm. And wind energy is intermittent, so you will see that the amount of generation is going to fluctuate over time. More importantly, you will see that the green lines are sometimes above the black flat line and sometimes below. Whenever the green line is above the black line, it means that at that instant, the amount of electricity you're generating is more than enough to support your entire data center demand. And when it's below, it says that you're not generating enough to meet that data center's demand, in which case you're going to actually consume energy from the grid at that point in time. And grid energy, as we know, is not necessarily at this point zero carbon. It's going to generate some emissions. So whenever the green line is below the black line, you're going to generate emissions, and when it's above, you're not. Okay? The more important thing is the total area under the green curve is going to equal the area under the black curve, which is why over a 1 year period you are offsetting or generating enough to offset your consumption, so which is why we call it net zero. Okay? But net zero, as you can see in this case, is still going to generate some emissions. And this brings me to my point from the previous slide, which is true zero carbon really needs more fine time scale matching, where the green line is carefully matched to your black demand curve at all times. And to do this, you might really need to significantly over provision your renewables, which is quite expensive. Okay? Or you have to switch to zero carbon sources and nuclear, which is also quite expensive. But technology companies, as you may have seen in recent headlines, are beginning to do exactly that. Okay. So what I will now talk about are approaches that you can use to decarbonize your data centers. So all of what I was talking about so far are what we will classify as supply side methods. Okay? So this broadly falls under the category of let's switch to low carbon energy sources. Let's not change our operations of the data center. Let's just buy green energy and make our data center footprint low. Okay? And as I showed you, that's really challenging. So it's not a solved problem yet. So we started looking at what we call demand side methods, which is, can we modulate the demand, energy demand of our data centers to reduce emission? And I'll explain how you can do that in a bit. But the point of this slide is that we need both supply side methods and demand side methods to reach true zero emission, right? So industry has largely focused on supply side methods, right? So we're trying to procure greener electricity, but I'm going to make the case that you really need to look at your demand as well and your operations and modulate that to reduce your emissions further. Okay? And the reason you can look at demand side methods is our computing workloads tend to be elastic in nature. And then the question is, can we exploit that flexibility in the workload to reduce our emission? Yeah. So what do I mean by this? Let me explain in two slides the sort of the high level idea. So the first slide here is showing you a graph, which is what is called the carbon intensity of electricity. You may be familiar with this graph. The x-axis is time. The y-axis is carbon intensity, which is the carbon emissions per unit of electricity consumed. And there are three curves there from three different regions, Ontario, Canada, there's California and Uruguay. And you will see, first thing you will see is that the graph is fluctuating over time. Right? So that means that how green your electricity is not constant. It's going to vary based on where the electricity is coming from, and the fluctuations in carbon intensity are going to be significant over time in many regions of the world. The second thing, you will see that different regions have different amounts of carbon intensity. Ontario, in this case, has lower carbon intensity than, let's say, California, which means overall the grid there is greener than the California grid. Okay? So there are two types of variations here. There are temporal variations in carbon intensity of electricity supply and spatial variations. And the idea is, as can computing workloads exploit these types of variations to reduce their carbon footprint? Okay? And the basic idea is you should run more workloads when the carbon intensity of energy is low and reduce less when it is high. Okay, so that's going to allow you to do the same amount of work but reduce your carbon emissions. Or you want to shift your workloads to regions where greener electricity is available. Okay, so these are some ideas I'm going to sort of talk about in more detail in the rest of this talk. Okay, so that's essentially the carbon intensity of electricity. And what I wanted to say also is that there are other things you can do with this, not just optimize your cloud workloads. This figure here shows essentially Apple's iOS home app, and it basically now has a feature called Grid Watch that's activated in many countries, not all, but it gives you a grid forecast. It tells you what time of the day your electricity is going to be greener. So the idea is you can maybe do your laundry there or charge your electric vehicle when it's greener, exploiting that same idea I was talking about. So you can use this idea in other domains as well, is the point I wanted to make here. Okay, but coming back to cloud workloads, I also said they're flexible. So what kinds of flexibility might we be thinking about? So different workloads will have different dimensions of flexibility, but by and large, if you look at batch type workloads, which are quite prevalent in cloud environments, you will see that there are different dimensions that I have mentioned here. The first one, of course, at the top just says do nothing. When a job arrives, just run it immediately. The second one says run it elsewhere, maybe run it in a greener cloud region. The third one says run later, which says maybe you don't run the job as soon as it arrives, wait for a time period when carbon intensity is lower, run it at that time. Okay, then you can run it slower, run it faster, run more intermittently. So there are all kinds of things you could do in terms of scheduling that job to essentially exploit this flexibility. Okay, and the idea is depending on the dimensions of flexibility you have available for a particular workload and the carbon intensity variations that you might see, how can you match the two and modulate your demand to reduce your carbon footprint? That's really the basic idea that you should take away from this talk. And I'm going to now explain in a little more detail how you can do some of these things. Yeah. So, but let me now introduce our project, which is called CarbonFirst. We started working on this 4 years ago, and the goal of the project was to essentially make carbon efficiency a first-class system design concern. Okay, so we design our systems to be to have better performance, maybe better reliability, better energy efficiency, and our take here was we should really be thinking about carbon efficiency as a design goal as well. Okay, and so we said, what do we do to make all of that work? First, we have to expose energy and carbon usage of your applications, provide control mechanisms to your application or system designers, allow flexible policies to be implemented, and more broadly promote this demand side method. Okay, those were the goals of the project, and I'm going to give you some glimpses of what we have done to hit some of these goals in the rest of this talk. Okay, so let me start with some of these ideas. So I already mentioned the basic idea that CarbonFirst actually exploited, which is availability of green electricity over time and regions. Okay, so the idea is to do what is called workload shifting. So you can shift your workloads in time, not all of them, but some workloads can be shifted in time, other can be shifted across regions. And then by exploiting either temporal or spatial shifting to match the variations in carbon intensity, which are again shown in this graph to the left, you can essentially design greener cloud applications. Okay, that's really the basic approach. And now let me explain some of the details. Okay, the first question is you really need to know the carbon intensity of electricity supply. Okay, this equation here is just showing you how you calculate the carbon intensity of a toy grid, where maybe 25% of the electricity comes from coal, 75% comes from wind. Each of these sources have different amounts of carbon intensity. The carbon intensity of supply is the weighted average of those two. Okay, and then essentially lower carbon intensity means greener electricity. Okay? Now our question is, or the research question we want to ask is, can we actually predict what the future holds? You might know what the current carbon intensity is of your electric supply, but what is it going to be in the future? If you're going to schedule your workload, you might need to know that. Okay? So to do this, we built a prediction tool called CarbonCast. It essentially uses a machine learning based time series forecasting method. It uses a two-tier ML architecture, which the first tier looks at sources and predicts the amount of generation from those sources, and then the second tier essentially predicts, gives you a 96-hour forecast, just as your weather forecast for the next day and 2 days from now and so on. CarbonCast will give you 4-day forecasts of what the carbon intensity is going to look like for that region. Okay. And then there are some results here. This is an open source tool, incidentally. You can download it and use it in your work, and you can use the predictions for performing scheduling or any other optimization. But by and large, what our result showed is CarbonCast is very good at near-term forecast. Like if you want to predict what the carbon intensity is going to be 24 hours ahead, it does a pretty good job. Errors are low. But as you look further and further out, 2 days out, 3 days out, 4 days out, the errors begin to grow. Okay? And this is very similar to weather forecast, where maybe the near-term weather forecast is usually pretty good these days, but a few days out, maybe the weather forecast might change over time. So there might be errors in them. And we are seeing similar results for our carbon forecasting. Okay? And that's the first thing I wanted to say, and that's shown in that curve here where it shows the carbon intensity of California. Different colors are different day ahead forecast, and you will see as you forecast further out, the errors are actually growing. Okay? And then our errors also varied across regions. We were within 5 to 15% across regions, depending on how much variation there was and how good a job we could do. But by and large, we felt like this was still good enough for us to take as the input to some of our scheduling approaches. Okay? So that's CarbonCast, which allows us to do carbon forecasting. And then what we did is we built a system that could then use this forecast to enable applications to do interesting carbon-aware optimization. Okay? So I'll explain now our system, which we call EcoVisor. Okay? EcoVisor is an energy hypervisor, and I'm going to explain what that means. You might have heard hypervisor and virtualization in a more normal systems context. This system is actually trying to virtualize your energy resources. And to motivate this, I'm going to explain it with a very simple idea. The figure here is essentially showing you the abstraction provided by the electric grid. Okay? So on the left, you see an electric socket. Okay? That's your interface to the grid. You plug in anything you want, your computer, your appliances into that socket, and you get a reliable supply of electricity. Right? So a grid abstraction is very simple. It's a socket. It just provides you a reliable source of electricity. It's completely opaque in terms of where this electricity came from, what might be happening inside the grid. None of that has ever been exposed by the grid to end users or computing applications. Okay? Now, what EcoVisor does is it breaks this simple reliability abstraction and tries to expose the grid dynamics to applications so that they can use them for performing carbon optimization. Okay? The first thing you need to expose is not just that you have electricity supply, but how green is that electricity supply. So you need to expose the carbon intensity of electricity and perhaps future forecasts. And those are the top two curves there, which shows where the electricity might be coming from, what kind of carbon intensity it basically has at any given time, and so on, as well as other types of grid resources like storage that might be present nearby. All of this is actually exposed through EcoVisor to end applications, which then allow them to perform different types of carbon-aware optimization. Okay? So that's the high-level idea here behind EcoVisor. And so you are essentially providing more visibility into what is happening in the grid, and then you have control mechanisms that allow you to control your energy and carbon usage. Okay, that's EcoVisor. Here's a sort of a figure that shows how EcoVisor sits in the hardware software stack. So the way you want to think about it is it's basically sitting next to your hypervisor, which is virtualizing your traditional resource list like memory, CPU, disk network, and so on. Your EcoVisor that sits next to it is exposing virtualized versions of energy resources, electricity supply, renewables, energy storage, and so on. So now applications which are virtualized get to know not just their resource consumption, but they also can figure out their energy and carbon consumption. And an ecovisor has interfaces which are shown in that table in the right. I'm not going to go into the details there, but just what the table is showing is there are mechanisms that allow you to control your carbon usage. So for example, you can say, here is a cap on the carbon this application would like to place, and then through a combination of the ecovisor and the hypervisor, you can essentially ensure that the application never exceeds its targeted cap, or there may be a carbon rate. So there are all kinds of things you could do once you have a system like an ecovisor. Okay, so let me now show you some of the neat optimizations we can do with the ecovisor. Okay, the first thing I'm going to talk about is time shifting. I briefly spoke about this when I was presenting the concepts earlier. So what time shifting does is essentially it takes a batch workload and it tries to run that batch workload whenever the carbon intensity of electricity supply is low. Okay, that's shown in the first graph there, but the x-axis is time, the blue curve is carbon intensity of electricity. Okay, and you will see the valleys. So valleys are in that curve are when the carbon intensity is low. So you take a batch workload, you use suspend and resume. So whenever the carbon intensity is high, you suspend the workload. Whenever it's low, you resume it. So it's running whenever you have green electricity available. Okay, through a suspend resume approach. And this approach is called wait a while. It was developed by some researchers in Germany, as it turns out. And they showed that by performing this simple suspend resume approach, you can reduce the carbon intensity of that, not carbon intensity, carbon emissions of that job by up to 30%. Okay, same job. Now it's basically running whenever green electricity is available, and you reduce just carbon footprint. Okay? Now we looked at this idea and said that's really neat, but the problem here is you're significantly increasing the completion time of the job, because there are long periods where the job is not running at all because the carbon intensity is high. So the job is going to take much longer to finish, even though its carbon intensity is low. Right? So we said, can we use ecovisor to do something better? And we said, why not actually use a different approach, which we will call scaling, to essentially exploit this carbon intensity variation. And the idea here is, because the carbon intensity is fluctuating, rather than suspending and resuming jobs, why not just change the amount of resources you allocate to it? So when the carbon intensity is low, you are going to actually scale up the job, give it opportunistically more servers so it can compute faster. And when the carbon intensity is high, maybe you will reduce it, not necessarily down to zero, but you'll reduce it so that it consumes less resources and has lower carbon emissions. And a toy version of this is shown in the right graph, where the black curve is essentially the amount of resources you allocate to a machine learning job and a training job, and the red curve is essentially the carbon intensity. And you will see that whenever the red curve is low, the black curve is high. So essentially, when the carbon intensity is low, you are giving that machine learning training job a lot more resources, and vice versa. And by using scaling as opposed to completely suspending the job, you can actually run it much faster and yet get reductions in your carbon intensity, carbon emission. Okay? And I'm going to show this in more detail on this slide here, which is talking about two applications: PyTorch machine learning training and BLAST, which is a scientific application. There are many bars here. There's a carbon agnostic policy, there's wait a while, which is the system policy, and there are two bars that are essentially scaling using ecovisor. The white bars are carbon emissions, lower is better. Okay? And the pink bars are essentially the time the job took to complete. Again, lower is better. You will see that carbon agnostic do nothing policy has the highest carbon emissions, but the fastest completion time. The second set of bars are wait a while. You will see that the completion time, the pink curve, is very high, which means that suspending jobs takes a long time, but the carbon emissions are low. Okay? And the other bars are various ecovisor policies. So what that shows is, by scaling jobs, you reduce the completion time is completing much faster, but you're also getting emission reduction. Okay? So by carefully constructing these policies, you can get a much better trade-off between the completion time and the carbon footprint of that job. Okay? That's essentially one of our results. There are many more that I'm going to skip in the interest of time, but essentially talk about what are some open challenges in this area. Okay, so I talked about EcoVisor and I talked about CarbonFirst, and we spent 4 or 5 years on this problem, and we barely scratched the surface, right? I mean, there's a long way to go before we can make our systems truly zero carbon. Many open challenges. Hopefully, some of you will be interested in working on this. How do you generalize beyond cloud workloads? How do you make the network greener? So the internet and many other types of network like data center networks also consume energy and have a carbon footprint. How do you make that greener? Can we actually generalize beyond cloud and computing altogether, apply these ideas to other domains? How do we actually do that? Right? How can we do better by changing trade-offs? Right? There are many kinds of trade-offs that arrive here. The main thing is you should remember is there is no free lunch. You make a carbon emissions of an application lower, you are going to have to make a trade-off in some other dimension, whether it's resources used or the time it takes to complete and so on. What kinds of trade-offs can we exploit to get a better balance of emissions and other kinds of things that the applications care about? But the more important takeaway here is I only spoke about what we call operational carbon, which is the carbon footprint of the application when it's actually running. But there's another type of carbon footprint, which is called embodied carbon, which is the carbon that you have in the hardware and the life cycle of that system and so on, which I didn't talk about at all. That's also an important problem that we should be thinking about. So what we have done now, having actually almost wrapped up the CarbonFirst project, is actually started working on another project which is called CODEC, which called computational decarbonization. So this is actually going to continue where CarbonFirst left off. This is a much bigger project than CarbonFirst. It's a center scale project that spans actually 6 universities, including UMass. And the goal of this project is to really think very deeply about this field of computational decarbonization that's emerging, and try to think about how can we optimize and reduce the life cycle carbon emissions of all kinds of complex infrastructure, not just computing infrastructure, but also things like the grid itself and buildings and maybe supply chains, manufacturing, agriculture. So many different domains, trying to think about how computational techniques can apply to this broad set of domains. Okay? So this is a project that just got started maybe a few months ago. As it turns out, Keshav was kind enough to write us a support letter when we had written this grant proposal. So we think of Cambridge as being an international partner in this project. So I'd be really happy to talk to all of you about what you think should be areas that we should work on and perhaps even work on together. Right. So I'm going to wrap up and leave some time for questions because I was told to leave maybe 15-20 minutes for Q&A. So what I want to say is the problem that I talked about in terms of the carbon footprint of data centers and cloud is still a significant problem because of AI workloads. And what I showed you today was how can you exploit the elasticity or flexibility of computing workloads to reduce their carbon footprint through simple scheduling techniques. But many significant challenges remain, and we will need to work on them to address this climate change issue in the coming decades. So I am really looking forward to seeing what ideas all of you have at Cambridge on this problem. But I do want to end by pointing you to 2 videos. We actually made 2 videos on CarbonFirst. They are going to be advertised during the COP29 climate summit that's going to kick off in 2 weeks. I put the links of those videos here. I'll be happy to share the slides after with Keshav, so you don't need to really write this down. But do take a look at how we are trying to explain this problem to a broader audience of the broader public, not just a computing-oriented audience. So with that, I'm going to end it here. I want to acknowledge all the students who and other collaborators who worked on CarbonFirst. They're all listed here, and there are 2 websites here in case you want to look at our papers. Okay? So with that, I'm going to stop and take questions from all of you. Thank you very much.
Thank you. For excellent time management, you have lots of time for questions. I think Anu was first, and then John, and then Ian.
Thank you. That was a brilliant talk. Thanks so much. So I looked into eco-filter cell techniques about 15 years ago at the Zen and later on at the Docker level as well. And the problem we ran into was that if you're doing suspend resume at a process level, that you tend to slow down these batch jobs running because data locality is a key part of how they schedule things. So if I suspend something, then I'm forced to keep the data alive in that machine. Then you can't schedule other jobs that need to do things. And so overall, your big workloads, especially MapReduce style workloads, were kind of badly affected. So is that the right level to be working on at all? Whereas if you go up these days to Kubernetes and these sort of levels, and indeed to the API levels where the application can make more intelligent choices, then that seems much more likely to drop the overall carbon usage rather than inserting something into the lower levels of the stack. So I'm just curious on your views on where this should go next.
Yes, excellent question. Actually, that was the ecovisor approach. It was inspired by exokernel and many other systems that you are talking about that really wants to empower the application. So basically says the system level policies or one size fits all by putting this lower into the system is not necessarily the right approach. Applications have different levels of flexibility. So this is best done by policies that applications can implement, not necessarily in the application code, but maybe through application level schedulers and other techniques. So indeed, we have actually put some of this into Kubernetes. The ecovisor paper was advocating for application level carbon management. And some people in the systems community really pushed back saying that's too much because application developers are never going to want to really write code to manage carbon. They have enough problems trying to make their applications performant. So there's a lot of back and forth, but that was really our view as well, saying that the more you empower the applications or the customers to implement their own policies, maybe the cloud provider should not dictate one carbon policy. They should let the cloud customers figure out what makes sense for them and have ways to implement those policies on the cloud. That was really our take as well, actually, as it turns out. So you're spot on in asking that question. Ecovisor was not actually trying to say the policies at the ecovisor level. It was merely providing mechanisms that allowed you to implement these policies higher up in the stack at the application level, just to clarify what the ecovisor system was trying to do.
Yeah, thanks. That totally makes sense. And these reviewers, if we don't manage our carbon at the application level, we'll have bigger problems, right, than those applications. So it seems that was a really poor reviewer response. So thank you for that.
Well, the paper got in, so I won't blame the reviewers, but they.
John. Yeah, I was just going to mention, I examined a PhD in Helsinki where they put a data center on the roof of the building and put it under a perspex tent, and they grew tomatoes and peppers in the tent. And they said this was negative carbon because they were able to sell the tomatoes to people instead of having them flown into Finland all year round. They're growing them locally, so they were carbon offsetting that amount of waste and carbon emission were flying in. But no, it was pretty cool. They also actually had power usage efficiency. It was really great because the whole thing was air cooled, just it's very cold.
Right? I was one of the other.
Yeah, you were at the And it was a really cool. It has a paper which is what plants can you grow that you have useful food. Where you only have about an hour of daylight for 6 months. Yeah, but you can keep warm because they're in a data center.
Yeah. No, I think I'm aware of that work as well. All of us are actually, we saw those papers back then when they were doing all of the school work. But back to your point, John, the issue is really we got to be thinking not just energy efficiency, but carbon efficiency. And yeah, if you can actually make it carbon negative, as you're saying, which is you're actually reducing the carbon impact even beyond what the consumption is, that's really where we should be hitting. And to be honest, I think having this conversation with industry has been quite challenging because they have their own viewpoint on this as to what they should be doing. At the moment, they're all engrossed in trying to become the top dog in AI. So they're really not as worried about sustainability as they were even 2 years ago. So now the conversations have changed and they're really going backwards, if you will, in some way, in terms of where they should be thinking about some of these problems. But as academics, I think we will continue to push, and we should all do that to make sure that eventually all of these ideas do get adopted.
Thanks.
Thanks for a great talk. Have you looked I mean, I assume it depends where you are in the world, but have you looked at the correlation between the spot price of electricity and carbon emissions?
Yes, very good question. I think that's a paper we have not written, but we did look at that analysis. And the short answer is there was not a lot of correlation because spot prices, at least whatever was exposed to the end user or customers by cloud providers, was actually more driven by demand as opposed to carbon emissions because carbon emissions were still not exposed directly to end users. So very few customers are optimizing their workloads based on carbon intensity variations. However, they are optimizing their workloads or provisioning resources based on the demand that they see from their end users. So a lot of the spot prices fluctuations was more related to demand periods, and I mean workload demand, not energy demand here, and that might not be completely correlated to what's actually happening in the grid. So the correlation was not there. I mean, it was really weak or at some level.
I just need to clarify, were you looking at the spot price of electricity or the spot price of site?
Oh, excuse me. I thought when you said spot prices, you meant because we are talking about cloud, you meant spot prices of server instances. If you're not talking about spot prices in the grid, that's a different problem altogether. That we have not actually looked at yet. In fact,
In the UK seems to be a fairly strong correlation.
yeah, I would not be surprised by that because as you have more and more renewables and there is fluctuation, the spot prices will actually get more correlated to carbon intensity, which is also correlated to the amount of renewables in your energy mix. So I'm not surprised by that, but we have not looked at that.
I don't know. Again, in the US, are cloud providers themselves paying spot prices for electricity, or are they paying constant prices?
Yeah,
They wouldn't care.
that's a good question. So what all of these big tech companies are doing is they are trying to essentially bypass the grid altogether, and they're going directly to the supplier, wind farms, solar farms, and entering into 5, 10, 20-year contracts to directly buy or procure electricity. So all of these tech companies are very big energy markets and procurements group that all that they're doing is saying, where can we buy more green energy? And the way it works, at least in many countries, including the US, I don't know as much about Europe or the UK, is you can, as a consumer, enter into a direct agreement with the electricity supplier. You do not have to use the electricity mix that your electric company provides. So you can go directly to the source and procure them. So a lot of them are actually not looking at spot prices at all. They are going one step further and saying, you are a wind farm, I'm going to just buy the next 5 years of your generation, and let's just sign a contract. Right? And that's how they are going.
Thank you. Hey, this is quite closely related to what you were just saying, but I was reading recently about how Microsoft bought, I think, the 3 Mile Island nuclear plant, which just seemed like a really crazy headline to me. Do you think you might see more moves like that on the nuclear side? And is that a step in the right direction in terms of decarbonization?
Yeah, it's a million-dollar question, literally, or maybe billion-dollar question in this case. So Microsoft is not alone. So I think Microsoft made big headlines, but barely 1 week later, I think Amazon and some other companies jumped into the fray and they signed other contracts with other nuclear companies. So at least in the US, it looks like nuclear is going to come back in some way or shape or form because the tech companies, what they're finding is there is no more green electricity they can buy. They have gone and bought whatever wind farms are in operation or under construction for the next 5 years, next 10 years. So there isn't capacity they can actually buy. So what they said is nuclear energy seemed like an untapped source. There are plenty of money, clearly. So they started looking at nuclear as an option. Now, in terms of low carbon source, certainly it's low carbon. It may not be the environmentally most friendly source because it does generate nuclear waste and whatnot, but it is low carbon. It is very stable. So you will not see any of the problems you see when you have wind or solar or even hydro for that matter. So if there were abundant nuclear energy available, some of what I was talking about may not actually need to happen. You may not need to change your operations because the carbon intensity of your electricity supply will be stable because nuclear is a stable source. So, but we are a long way off, right? I mean, we're still decades away from any one source becoming a dominant source. But the initial moves from Microsoft and Amazon and others seems to indicate that they will invest in wherever they can find green electricity, and they have come to a conclusion that nuclear is one of them. And I think we'll see more nuclear deployment happen as a result, at least in the US. I mean, there is, of course, all these regulatory issues you have to deal with when you have a nuclear power plant, but somehow it's come back to life out of nowhere, at least here.
Yeah, going back to your system policies for shifting energy usage, it definitely makes sense that the time gets better when compared to this wait a while approach, but obviously that the carbon efficiency also improved, kind of like what Anil mentioned earlier too, with the idea of like, let's say cache misses or other type of context switching costs, like you can kind of intuitively think of a reason. Did you all look into that at all? If there anything else happening on the system level that could have caused
Yes.
this difference?
Yes, actually, I skipped a slide. So there's actually a very interesting, let me see if I can bring that slide back. Give me a second here. So the short answer is yes, I think there is actually a very interesting trade-off there. And I'm going to show this slide that, hold on one second. Yes. Okay, so let me just share this screen again. Do you see my screen now?
Yes.
Okay, so I think you brought up an interesting systems problem because there's I talked about suspend resume, but I also talked about scaling, and I said when there is low carbon energy, scale up the application. But it's easier said than done because just because you give more servers to an application doesn't mean its throughput is going to grow linearly, right? There are all kinds of scaling issues, hardware bottlenecks, caching problems, synchronization bottlenecks that will actually give you non-linear or sublinear scaling, which is what this curve is showing. So just throwing more resources at an application when low carbon electricity is available actually reduces your carbon emissions some, but it may actually make carbon efficiency worse because scaling is non-linear. So there's a very interesting systems problem for different applications, what is the right scaling policy that allows you to make the best use of these fluctuations in carbon. And we have one paper on this topic. It's just called Carbon Scaler that looked at this for some specific applications, but for different applications, you might need different policies. So it's actually a very rich area of research because this comes back to performance and how you scale up, and now it's tied to carbon footprint as well.
Thank you. We have time for one last question. Is anybody also, let me tell you, somebody online, anybody online has a question, you can unmute and ask, or otherwise you'll ask another question from the room. Okay, and
just going back to your prediction of carbon intensity, you're using the CNN and the LSTM for that. So Google recently had a really interesting paper on combining both computational models that are differentiable with past data. So the insight here is that the data will help you predict stuff that happened in the past, but the computation model can help predict the black swan events in the future, so the big surges. And for weather prediction, that's been an order of magnitude better than using either just a pure data-driven model with a predictor or a pure computation model that goes chaotic. So do you think there's any legs in the future work on creating a differentiable computation model of where demand sources are coming from? So you get people saying, these are my energy sources and these are what I'm predicting computationally, and then you use the actual data from the grid to predict the past. Because that would give you the ability potentially to predict, say, a day in advance for where the carbon energy prices are going to go, and then you could do enormous optimizations, obviously, with that kind of window. Whereas otherwise, we're working with a few seconds or minutes at most, I assume, for the predictions.
Yeah. So first of all, our carbon predictors are predicting 4 days ahead, not just minutes or seconds. And there's companies like Electricity Map and What Time that are also giving you 1 or 2 day prediction. So already predictions are looking at 1 to 2 days, but we still don't think that is enough because there are jobs like ML training that takes weeks to complete. So you might need much longer term forecast than what we have. So, and our 4-day forecasts are not great, giving you 15-20% error. So clearly there's a lot of room for improvement. I was not familiar with this Google paper that you are just mentioning, but certainly carbon forecasting is a rich area that can actually use better forecasting model, just as there has been so much work on weather forecasting for decades, and we're still making improvements. I think this kind of stuff will actually be applicable to even carbon forecasting. And perhaps 1 day actually at this point is not bad. You can get within 5%. In many cases, the error is 2-3%. So there's not a lot of room to improve, but 2, 3, 4-day forecasts, I think there's certainly a lot of room to improve. Just as weather forecasts are getting better as you try to do few days out, we can also do the same here. And I would be actually interested in getting a pointer to this paper so we can look at it in more detail to see how to apply to this type of problem.
So I'll send you an email with the paper. Thanks so much.
Great, okay, we are out of time, so Prashant, thank you very much again for taking the time. A very interesting talk, and I'm sure you'll be hearing back from us for that.
Thank you, Keshav. We'll be in touch as well about the project. Thanks to all of you. Bye-bye.